All right, welcome back, everyone. In this section, we're going to talk about exponential functions. So in this section, you're going to learn what an exponential function is, how to determine the graph of an exponential function, how to determine values of exponentials using your calculator, and how to determine compound interest and other applications of exponentials. At this point, for the rest of the chapter, you will likely need your calculator, so keep it handy. So up to this point, we've only dealt with polynomials. Exponential functions are named because the variable is in the exponent. So for example, a polynomial would be something like y equals x squared, whereas an exponential function would be something like y equals 2 to the x. Notice the x is part of the exponent. In general, exponential functions are just written as y equals a to the x, where a is just some real number and x is the variable. So in general, our exponential function should look like y equals a to the x. So when we talk about graphing exponential functions are one-to-one functions. If you go back and look at the end of the video from the last section, the one-to-one function that was graphed in example 5.1.4, that's an exponential function. Exponential functions are one-to-one. Exponential functions can never be less than 0 unless you subtract some sort of constant. Graphing exponentials in a general sense is hard because of the one-to-one nature. Every value for x is going to give you a different value for y. So you can't use symmetry like we did when we were graphing parabolas. With exponentials, every point is different. So the key to graphing exponentials is to basically make a table. Pick some x values and solve for y. And use the calculator to solve it if necessary. So let's say we want to graph the function y equals 2 to the x. What we're going to want to do is make ourselves a table. Our function is y equals 2 to the x. And so we're going to make a table where we just pick some x values and solve for y. And so let's say x is just -2, -1, 0, 1, and 2. And now we're going to plug these numbers in for y. 2 to the -2 power is the same thing as 1 over 2 squared, which is 1/4. 2 to the -1 power is 1 over 2, which is just 1/2. 2 to the 0 power, anything to the 0 power is 1. 2 to the first power is just 2. And then 2 to the second power is 4. So throughout that table, we were just plugging in the x values as exponents for 2. So now we have our points. -2 and 1/4. It's about right here. -1 and 1/2. 0 and 1. 1 and 2. And 2 and 4. And we get a graph that looks something like this. It's an exponential graph. Now the left-hand side looks like it's horizontal, but notice as x becomes more negative, this line's just going to get closer and closer to 0, though it'll never quite reach 0, nor will it ever cross 0. So it does get smaller and smaller, but it's just such a small change that it's hard to see on the graph. So exponential functions are really useful in describing real-life situations. Given the function that models a certain situation, we can learn things from the equation. So the next example, we'll talk about how exponentials are used in general, and then we'll follow it up with some more specific examples of what we can do with exponential functions. So, the number of pages in the IRS tax code has increased from 400 pages in 1913 to 70,320 pages in 2009. That increase can be modeled using the exponential function shown there. where x is the number of years since 1913. We want to use this function to estimate the number of pages in the tax code for 1950, 2000, and 2015. We want to round to the nearest whole number. So what this means, we want to start off and we have to figure out what our x values are. Well, x is the number of years since 1913. So our first x value is 1950 minus 1913, which gives us 37. Our second x value is 2000 minus 1913, which gives us 87. And then the third is 2015, which gives us 102. And so those are our x values. We just want to plug them into the function, and we're going to have to use the calculator to find these answers. So after we've found the x values, we're just going to say t, okay, and our function is this, t of x is 400 times 1.055 to the x power. And so t of 37 is going to be 400 times 1.055 to the 37th power. Remember your order of operations, you should always do the exponents first. And so in your calculator, you would type 1.055 raised to the 37th power, and you're going to get 400 times 7.25, which gives so in 1950 there were about 2,900 pages. Now if we do the same thing for the next two x values, we had 400 times 1.055. Now raised to the 87th power, that's going to give us 400 times 105.43. And we get 42,172. And finally, for our final x value, we're going to do 1.055 raised to the 102 power. That's going to give us 235.37. And then multiply times 400, and you should get 94,148. So we had to calculate the three x values based on the time, but then we were just able to plug it into the equations and solve. Now, one definite use of exponential functions is what's known as compound interest. Okay, so if you invest some money in the bank, how much money are you going to have at a later time? So this compound interest is given by the compound interest formula, which is shown in the middle of the page there. And it will determine the amount of money that you have at a future time, which is A, based on the principal, how much you invested, times 1 plus the interest rate, which is R. Now, in your problems, the interest rate will be given to you as a percent. Always convert it to a decimal. R should always be a decimal when you work with it. And R divided by N, which is the number of times the interest is rolled over, and we'll talk about that in the next slide. And then raised to the power of N times T, where T is the amount of time that's gone past. And so we'll use this formula in just a moment, but first let's talk about what N is. N is known as the number of times that this money is compounded. So after a certain amount of time, your bank will take the money you've earned in interest, add it to your bank account, and roll over to the next time. Depending on the account that you use, depends on how it's compounded. So if we compound the interest annually, that means N equals 1. That means we compound the interest once per year. So at the end of the year, your interest is added to your account, and it starts back over. If we compound semi-annually, then n's equal to 2. If we compound quarterly, then n's equal to 4. Monthly, n's equal to 12. And daily, n is equal to 365. In this case, n will always be given in words in the problem. It'll never be given in numbers. You have to know the words and be able to associate the numbers with them. 4 out of 5 of those should be easy to remember. Semi-annually might be a little confusing. So let's practice this. Suppose that we invest $82,000 at 4.5% interest, compounded quarterly. First, we want to find the function for the amount to which the investment grows after t years. So when we want to find the function, all that means is that we want to take what we know and plug it in. So we know the future amount is equal to the principal times 1 plus r over n to the nt. This is our compound interest formula. And what we know from the problem, we know that the initial amount invested is $82,000. We know that the interest rate is 4.5%, but remember, we always need to write it as a decimal, which in this case would be 0.045. And we know that it's compounded quarterly, so n is equal to 4. And so now we just want to plug all this stuff in. The future value is equal to 82,000 times 1 plus 0.045 over 4 to the 4 times t. We can simplify the thing within the parentheses by saying 0.045 divided by 4, and then plus 1, and we get 1.01125 raised to the 4 times t. This would be our function. On problems like these, don't round until the very end. If you round early, you might wind up missing the answer by just a little amount, so by a decimal place or two. And the computer will count that wrong. So don't round until the end of the problem. But here's our function. We now want to do part B. We want to find the amount of money in the account at t equals 0, 5, and 10 years. And so if we just go to the next slide, starting with our function, 82,000 times 1.01125 raised to the 4 times t. And now the future amount when t equals 0, we're going to get 4 times 0. Well, that's 82,000 times 1.01125 to the 0 power. Anything raised to the 0 power is just 1. And so we're left with 82,000. And that should make sense. When t equals 0, we just invested the money. And when you just invest the money, you should have $82,000. That's what you started with. After 5 years, now we get 4 times 5. Well, that's 82,000 times 1.01125 to the 20th power, which is 82,000 times 1.25075. And so after 5 years, you would have $102,000, $102,561.54. And finally, we would do the same thing for 10 years. When we multiply the exponents this time, we would get 4 times 10. which would give us 40, which is 82,000 times 1.56 4377. $128,278.90. So after 10 years, you would have $128,278.90. Now, if we then change the number of times that we compound money, right? So instead of doing it daily or quarterly or once every few months, let's suppose that we invest $1 at an interest rate of 100% at a time for 1 year. So if we do that, our formula just turns into that thing at the end there, a equals 1 plus 1 over n to the n power. If we then take this and start increasing the number of times compounded, right? So let's say n equals 10. Well, n equals 10, then the future amount that we have is going to be 2.59. If n equals 100, it's only 2.7. If n is equal to 10,000, it's only 2.71. If n equals a million, it's 2.71828. So as n gets bigger and bigger, as it approaches infinity, a is changing very little. Because of this change, we give this number a special name, this 2.71. The number that a is approaching is called the number e. So e is defined as the thing you see below. Okay? You don't need to necessarily understand what that means. But here's your decimal number. E is a lot like pi. Pi is a non-repeating decimal. E is a non-repeating decimal. Okay? It's an irrational number. Though it appears to repeat there in the numbers that are written, if you go to any terms past that, it's obvious that e doesn't repeat. E is a number that's very useful in modeling real-life data. And we'll talk about this in section 5.6. Graphs of y equal e to the x and variations of the function look just like other exponential functions, but they're much harder to get values. You're talking about raising a decimal number that never repeats to some power. So you either want to use a graphing calculator or some graphing tool to determine the graph of an exponential function. Okay? Plotting points is not as easy. You can't just pick numbers and get whole number values. So the last thing we need to talk about in this section is just how to find values using your calculator. If you look at your calculator, you likely see a button that says ln, and we'll talk about that button later. But for now, above that button as a second function, you should see something that says e to the x. That's what you're going to use in order to calculate e raised to some power. And so, rounding to 4 decimal places, if you do e to the 2.34, and you should use this to check what you're doing in your calculator, then e to the 2.34 is going to give you 10.3812. E to the minus 1.34 should give 0.2618. And then e to the 0.075 should give you 1.0779. So use your calculator and make sure that you get these same values. So at the end of this lesson, you should be able to graph exponential functions, or at least recognize the graph of exponential functions. You should be able to use exponential functions to solve applications problems, including compound interest. And you should be able to calculate values of e raised to some power.